Myself, Anish Singla, I am practice lead data sciences at Nagaro. She's my colleague Nikita, a data scientist at Nagaro. Since we are a little bit delayed, I'll just take 2 minutes to talk about Nagaro. So Nagaro is a global software services development company. We are about 25 years old, 6,000 employees globally in about 22 countries. We are seeing a huge potential in machine learning and AI. We have a dedicated 60 people team working on cutting edge solutions in speech, video, all kind of latest tools. And we are also hiring. So in case you are interested, get in touch with us. Okay, so quickly getting started on the topic. So yeah, it's about forecasting, a large scale forecasting for big retail chain, which has more than 6,000 products. And I want to share with you how we implemented things and what were the challenges we faced and how we resolved them.
Hello everyone, let's get started with the problem statement. If I want to frame my problem statement into one short sentence, that would be forecasting 150 plus products for 50 plus stores. Let's dive deep into the details of the problem statement. First of all, client had provided us with 5 years of forecast for sales data of different products from 2013 to 2017. Secondly, products in stores had different ages from as old as 5 years old to as young as 3 months old. SKUs could be in different stage of life cycle from introduction, growth to mature and decline. That I'll explain in the coming slides. Product sales are impacted by numerous factors. For example, what was the promotion or discount on that product on that particular day? What was the weather condition on that day? Then what are the competing products? For example, if we have a toothpaste for Pepsodent, then how many other brands are competing with that at that point of time in that very store? Then forecast is required for 45 days and it should be doable in less than an hour. Now, why do we need to forecast anything like sales? What is the benefit that business get out of it? First of all, inventory management. We can do our inventory management on the basis of systematic models rather than just depending upon the gut feeling or guesswork. Secondly, reduction in overstocking and understocking of goods. Thus, we are not underutilizing or overutilizing our resources. Thirdly, it is a critical input for supply chain management. If you think of any supply chain operation, first thing comes into mind, what will be the forecast of that very product on that day? What will be the sales that I'll be receiving? Then alongside you see the hierarchy of data which we had. The last two layers had the store, and the store is having n number of items. There is where we want to forecast our sales for. Next slide. So how many of you know the concept of time series? Can I see the hands? So it is a fair percentage. So I can get into the more details rather than just boring you with the basic concepts. Just explaining the trend, seasonal component and irregular component. It is just, if a time series is decomposed into 3 parts, it can be briefly done into trend, seasonal component and irregular component. Trend is either increasing or decreasing. It is not recurrent. Secondly, seasonal component, the third one you see, it is repeating itself after a period of time. That is the seasonal component. And last one is irregular component. If we extract trend and seasonality, irregularity is the thing we want to be left with. We don't want to be leaking any percentage of information into any of the residual. So if these are added together, we form an additive model. If multiplied together, we form a multiplicative model. This was the crux of the basic. Okay. Now, these are the methods which we use for forecasting. Are you aware of the methods that are listed here? How many of you are aware of them? Okay, those are pretty low. So, let me get into the details. First of all, ARIMA model. ARIMA model, let's split it into 3 parts, AR, I, MA. The AR is spelled as autoregression. Autoregression, let's split it further. It is divided into auto and regression. That means we are forming a linear model with the observation of the same variable. Like what is the observation at lag t with the we are finding the relationship with that very variable at the observation at time t minus 1 and so on t minus 2 and that. So we are forming a linear model between the lags that will cover the AR. I is integrated. I stands for integrated. It is the order of differencing which we want to do. That is, as we can read, subtracting an observation from an observation at the previous timestamp. That means we are bringing our time series to a same level. We are extracting the trend out of it. Okay, trend is handled here. Now third, as I mentioned before, we don't want to leak any information into our residuals. So if by chance any of the correlation between the lags is leaked into the residuals, then we also want to model it. So we are modeling the error at time t minus 1 plus the error at time t. So we are forming a linear model between the lags itself. T minus 1 and so forth, we can go to the, depending on the order of the MA we want. Second is the exponential smoothing. Exponential smoothing is relatively similar to AR, but it differs the fact, instead of finding the coefficients, we just assign some weights with the lags. Like as we go back in time, the weights decay. That means more recent observations are given more weights as compared to the older ones. So the weights are decayed back in time. Third one is dynamic regression models. Now, if we want to take the essence of ARIMA model and put some more regression external regressors with it, then we want to use dynamic regression models. We can just add holidays, weather conditions, and assign some coefficient to them and then add into our model. Fourth one, LSTM, long short-term memory. Then the neural network based approach, which include RN and LSTM. It uses neural networks. So this was the data which we used. It is briefly divided into two components. First one, data set shared by our client. Second one, which we sourced externally to help our model to predict something new trends, some new seasonalities. First is store master data. It has details regarding to the store, that is store number, which city it resides, which state, and the store type. Second is item master data, item related things. Here I want to mention the classes, like which type of product it is in. There is some sort of clustering done here. Third is sales data. So it has what is the sale volume at that particular day in that store for that item. And fifth, regressor we have on promotion, if it is on discount or not. Alongside you see the externally sourced data, which had holidays even for particular city. We had extracted for each city, when is the holiday, which type of holiday is it local, national, regional, that kind of things. Second is weather data, all temperature and humidity related things. So what were the associated challenges with our data set? First of all, we had huge variability in seasonality. If the products are seasonal, now let me tell you when the product is seasonal, it just appears to be reoccurring its pattern over a period of time. That is, for example, we can take winter clothes. Winter clothes are more to be sold in the month of November and December rather than in May and April. That will cover the seasonal products example. So the frequency of the seasonal product, that is after which it is repeating its pattern, that was different for each and every product. So that was first. And second, non-seasonal products. For example, if we want a broomstick, we get it no matter what we are using it. Non-seasonal products is those. So we had non-seasonal products. We don't know when is the pattern going to reoccur or is there any pattern there, etc. Second is we had some sales known as intermittent. Intermittent means we have products which had sales which can decay at any point of time. You don't know when it is going to be zero for a very considerable amount of time, and you don't know when it is going to touch the roof, the sales. For example, automotive parts, we can't just guess around when sales for automotive parts will be high and when it will be zero. It can be zero for a considerable amount of time. So that will be the example of that. Third one is handling sales of product in different stage of life cycle that I mentioned in the introduction. Alongside, you can see the snapshot of our own data. First of all, if the product is in its introduction phase, that is, we have very less data because it is introduced very late. The day of introduction, if you cannot see, is 20 April 2017, and we had data till August. So we had only data for like 3 to 4 months. That is the intro. We had very minimal data for these kind of products. Second is the example of product in growth state. You can see the peaks are higher afterwards as compared to earlier in time. So this product is touching its growth phase, is in its growth phase. Third is maturity. When we kind of know that, okay, this product will be sold at this range. This is the phase when the product is in its maturity phase. Fourth one, in decline phase. That is, the sales is declined, as very highlighted from the fourth graph. Now I would like to invite Anish sir to just tell you which approaches we followed and which worked for us and which does not.
Right. So these are the kind of challenges and the results with the first approach, which is the clustering approach. So we took all these time series that are there, all the 6,000 time series, and we extracted features out of these time series. So these features are like, what is the trend, what is the strength of trend, what is the linearity that is there, what kind of seasonality is present, what is the strength of seasonality, and so on. So there is a good paper by Robert Hindman, and there is also an R package, CRR package, which kind of automatically helps in extracting these features. So we extracted these features for all the time series, and then we clustered based on these 30 features to form similar clusters. So we got around 60 plus clusters, and we then aggregated all the time series within that cluster to form a higher level time series. And then we applied a hierarchical top-down algorithm to forecast within that cluster. So what this does is basically, it forecasts the top level series and also the bottom level series, and then it kind of regularizes both these series by making them coherent, so that the forecast is much more stable than considering a single time series. So that was the approach, and but the challenges that we faced in this problem was some of the clusters were very well formed. They had very similar time series, but some of the clusters were like not very well formed. They were like having completely different time series coming into them, and then we aggregated those the results at a lower level. For example, the first graph shows how the aggregated series look like, the forecast that is pretty much matching the the actual sales. But when we look at the a bottom level or a product level series, it's not very accurate. Also, this kind of approach is not able to handle new products and new stores. What if a new company comes up with a new store location or a new product? Then we don't have any historical data for that particular item, and we cannot extract any time series features to cluster. So that was the first approach. Now going to the second one, we would like to show like a detailed feature engineering that we did here. What are the different features that we came up with? So on the first one, so regarding the items and stores, we computed the age of the item and the store in weeks since the product was launched to see, because that was an important factor, that how long the product has been in market, to capture that. Then we, as Nikita mentioned, we also included how many competing products this particular product has. So we included that as a feature. We binned the ages from like A to E into different points using different points, so that that could give us a kind of a flavor of the life cycles that we saw each product goes through. Then we used holidays. So there were like holidays at different levels. We had maybe on the same day a national holiday and a local holiday. So we gave preference to a national holiday in that case. Then we used a lot of features for seasonality. So we saw a huge trend between like the weekday sales and the weekend sales. So we formed a day of week variable. Similarly, a week of the month was very interesting because people get paid in first week of the month, and the sales are generally higher that week. So we formed like 1 to 5 week of the month, and then to cover the monthly seasonality, we had a month variable which had like 1 to 12 value. Then in order to accommodate the trend, we used mean and standard deviation of the weekday sales, the weekend sales. We did it for two levels, like using the entire data and also using the just the last 2 months of data, so that we could give more weights to the recent trends. And then we took also the ratio of what is the weekend sales and versus what is the weekday sales. We also considered a moving average of 3 months as a feature that could give an indication of whether the sales are declining or whether the sales are catching up. For the promotions, we did some interesting things. So we already have a promotion at the day level. We kind of shifted the data so that we could form features like, is there a sale next day or was there a sale previous day? And we could also figure out how big the sale was, how many percentage of the products in a store were on the sale. So these kind of feature engineering gave more power to the model, and it can use these things effectively. Finally, we took the output variable, we took a log of it because that was giving a better accuracy, and also it kind of avoids any negative sales value while we are predicting. So these were the feature engineering that we did on the regular features to bring in a lot of things that the regular time series models use, to enable regression models to also have those, and build a huge set of external variables. So this is a quick thing into the how the data was used. So we didn't use 5 years of data. We just used 2 years of data, primarily because one was better accuracy, and because the last 2 years was more reflective of what the how the market scenario is. We used the last 45 days for testing data, and we used XGBoost model with 5-fold cross validation, primarily to figure out how many training rounds we should do, because XGBoost has a tendency to overfit the model. So we decided the training rounds using that, and then we trained on the full model so that we can utilize the entire data and the early stopping from the cross validation. And then we tested our model on the 45 days data to kind of baseline what the model performance is. Yeah, I think we have also organized a part of data on Google Cloud. So we have loaded the data into BigQuery, and we are using Data Studio and the ML Engine AI platform offerings from Google Cloud, and we have built a quick demo because it's always nice to see things in live, right? So this is the aggregated for sales. Here we are using a part of the data. The historical data is from 1st January 2016 to end of June 2017, about approximately 1.5 years. And then the last 45 days is the prediction period. So this is the cumulated sales for the past. And then if you could change it to the testing period, we could also see how the results look like on the 45 days. So this is the Data Studio dashboard. It picks data from BigQuery. And we see if we, we can also filter out by store and product. It will quickly aggregate those values and present to the user. So this is how the sales and the predictions look like. So the blue ones are the predictions, and the red ones are the actual sales. So we are able to quite well match the pattern, and to a certain extent the scale as well. In the second half, we also kind of, in order to enable more analysis, we have kind of included some of the external variables like, holidays and promotions, so that we can visualize the impact, in a combined form. So the y-axis here, the first axis is the sales, and the other dual axis is representing the promotion and the holidays. So the green bars are the holidays, and you see that, there are clearly a certain impact which the holiday has. Yeah, if you could just pick something. Yeah. So this helps us analyze that, right? That how the holidays are impacting. Maybe certain peaks are happening after the holidays, certain peaks are happening before the holidays. How are promotions impacting my sales? So this is kind of a high level, like a quick demo that we could put together. Maybe we can switch back to the slides. So we have a quick comparison of both the results. How things look like. Yeah, so we already saw these. We can skip them. Okay, a quick thing on the errors. So we saw that the errors are normally distributed around 0, which is good. There is no autocorrelation or partial autocorrelation in the errors, which means we are not leaking anything into the errors. Also a good sign. So this is the kind of a summary that, the execution time with the XGBoost was less than 1 hour, whereas the other approach took more than 3 hours. The root mean squared error was about 9.6. So on an average, we are kind of, not predicting the sales to a scale of 9. Whereas the other method, so there are some products where the forecast is very good and some where it is not very good. So the average is about 25. The scalability, as I mentioned, the XGBoost model is able to handle the new products automatically because there is no hard coding with respect to store or item. The number of models trained also varies with 1 model and 62 models. So I think we also have some slides about prediction interval and confidence interval, how those can be generated on these. But we would like to skip that and take time to answer any questions you may have.